Okay, that it's recording, and now I will share my screen. Okay, so let me show. I think it's yes. I share it. Okay, then I get again my I will hide slides. So we go back, hide slides, and that's it. And hide slides. Okay, so okay, we will revisit yesterday process analysis, and the point is just to remind that it was composed of processes, and each process was composed of operations. Okay, and but we need to define, in order to establish a hierarchy in the process that is a bit different from the hierarchy of a product. We need to define some functionalities. And as I said yesterday, there was a productive function that permanently changed the parameter of an object. Okay, so we contribute to the final state of the product or of the material. Remember, the definition of a process is a set of operations that transform one material, one product, whatever, into a final state. So we are producing something, either an information, either a grant, either a material, either a car, whatever. We are moving from an initial state of of elements to a final product, or initial set of informations to a final decision. All these are information. Or, as I said yesterday, a signal, we can shape this signal and end into a final signal. That can be also a process. Okay, so there was a productive function. This is the point of what really is moving our material, our initial state, to the final state. So it's very relevant in terms of functionality. It's very relevant. But many times, for these productive functions to move the product to the final state, we need many auxiliary functions that temporarily prepare or positions, or just make something that saves, that helps the productive functions to achieve their goal. And we say that temporary changes can be is always temporary. Auxiliary functions that changes are temporarily and can be again returned back to the position before. And we saw also that corrective functions. This was normally due to an auxiliary function. We need to go back. An excessive function, we need to remove some debris of our product, for instance, into a metal product, or for instance, for a chemical process, we need to remove some diluent or some catalyst. We need to remove it from our chemical process. So this is for processes, for any type of processes, for producing fuel, for producing a vaccine. Nowadays, that we are all racing for producing a vaccine, not for discovering yet, for testing the vaccine. Then we will face the problems of producing this vaccine in millions, enough to arrive. Okay, so eliminate and reduce undesired effects or harmful functions that we saw yesterday. Okay, maybe this was moved into a position, and we go back with the corrective and the harmful function, generating non-desirable characteristics or decreasing positive features. This is what we saw yesterday, and we talk about an example of industrial bread making that we talk about weighing, dough making, baking, cooling. Okay, and we saw what happened in the weighing. So each you see the point is we have operations, and within each operation we can describe it as a system, because each operation is like an island that the only connection is that the product in one operation is a super system that enters into the subsequent operation. So this is and this is why we can do it like this. Of course, we can put into list scales, control pump, ball move scales, etc. But as I said, we can do it like this: scales, control pump move ingredients, and the ball just get with enough quantity of ingredients, and when it weighs, just stop the control, the pump. Okay, and the dough making, we have here the interesting function of kneading, and the interesting function of the ingredients becoming a dough. Okay, a dough that we need to knead, okay, to have a good bread, as always. And then we saw the baking, that the gas flame was hitting the air, and this air was hitting the dough and releasing all the CO2 in the process, and just turning the crust, the outer layer, the crust of the bread brown, etc., and then just move getting out by the conveyor. But in this process, some of the air was heating, and this was hitting the dough, becomes the bread, and then the conveyor moves and gets out the bread, and there was some heating of the bread that was extra heating, and so we need cooling, and this is how we put this in a list in an Excel file, and can define if they are auxiliary or they are productive. We will see again, and the cooling we can say like this in an Excel file, and then like this. Okay, the conveyor moves the bread, and the air cools the bread. Okay, that's it, and maybe we can add packaging, whatever. Okay. Okay, so let's and we finish with this. There was this was I repeat the advice I gave you yesterday. There are very few in a process. There are few productive functions, because they are just the one that move to the final state. And most of them are auxiliary, providing auxiliary. So we're defining just who was providing. Okay, you can do this one and just put the arrows or whatever you like. It was productive. We're only becoming dough here and forming mix, and then becoming bread. This was the production here in baking, and just cooling was corrected, etc. Okay, so we started to see what can be the trimming here. Imagine that I just remove cooling. So maybe I sell. I have in my industrial bakery. I have a shop at outside of the bakery, and offer hot bread that is always very welcome to people. Hot bread all the day, so all day long. So if I remove cooling, then maybe I can have a less demanding and less energy, etc. But what if I remove? Try to be more aggressive and find a new type of uh, uh, process. What if I remove baking? What is baking in the end? If I remove baking, then my dough is just fermented and just goes, and I can sell, for instance, frozen pastries. This is what most of the supermarkets get. They get frozen pastries, frozen doughs, and they just let them get the ambient temperature and then put them into the oven. Okay, so you are selling at this point. But let's dig a little bit. Let's try to understand what happens, what are the functions that happens during baking. And let's see if we can find other alternatives to this baking. And let's see, what is baking? The function to bake is, I can say, you see, a dough is like a white or creamy, a cream color, and soft mass. Okay, you can knead it, you can handle it, etc. Okay, and when it is bread, is just crispy, it's brown, the outer layer, the crust, and it's plenty of bubbles in inside, and it's a bit elastic and inside, etc. So what is, if we are experts or not so expert, but we dig into the process of baking and we want to find new alternatives, we need to understand what functionalities are occurring. The same can be analyzed for instance, into a chemical reactor. What functionalities are there occurring? We have worked with some large company in the oil industry, and have helped to these people to understand what happened and how they could remove some part and pass from a catalytic reaction to a non-catalyst reaction with all the benefits that you need to remove the catalyst afterwards, some operations and no more operations. But let's go back to a more easy function, like is baking. What is baking? Is maybe is evaporating the water of the dough. The dough is wet, and finally the final bread is has of course has some moisture, but much less. Okay, so evaporating water is one of the functions I need to do. Are there all the other ways to evaporate water? Okay, this is one point. Maybe this is one point. Maybe there is also other functions. You may say, no, what about the proteins? You are not taking into account the proteins. What happens to the proteins? We polymerize the gluten. I mean, there are different proteins that get polymerized and become gluten. So how to polymerize gluten? Do we know different functionalities to polymerize gluten? Probably we can how to polymerize proteins. We can search into the internet to polymerize proteins and look how to polymerize special proteins that are present in the dough before it becomes gluten, and because it's the polymerization of such proteins, and we get the elasticity of the bread. Okay, the elasticity when we break the bread, and this mass just gets you know what I mean. Okay, so this is to polymerase gluten. And also we need a brown crust. Okay, so caramelize the crust. Why is it brown? Because we caramelize the sugars that are in the outer part, and these are caramelized. And do we know other ways to caramelize the crust? Sure. And I would add just let me add another one. Is sorry, is let me copy and paste, and then I put here to release CO2. Okay, this would be the last one. Okay, to release CO2. These are some of the functionalities. So if we analyze what happens and what are the functionalities that are the functions that are getting into the process, into any part, into any product, we can start to find new things. I would like you to retain this concept, because if you apply this, I'm sure that you will be able to change many things that we are just get for granted, and that's not the point. We should change things, and you have with knowing what's occurring in terms of functionality, you can find alternatives, and you can find probably new interesting processes. Let's see an example of in other sector, how people is understanding what are the functionalities of different element. Let me show you another process. Let me okay, no, let me go. No, what is okay? Let me show this one before, and then we will get. This is a ink making of a large company. You may see here the list of the functions: vessel holds varnish, varnish holds pigment, shaft moves blade, blade moves varnish, blade heats varnish. That's a harmful, pigment holds pigment. The pigment just is getting clogged and getting how I would say making crumbs, and so it's a problem they have. Okay, and body then bit milling. This is a milling, the milling with to just to make this pigment that is holding another pigment and making crumbs to just separate these crumbs and just destroy these crumbs. Beads hit varnish because we need to mill with the beads, and that's it. Finally, a roll milling for making a very thin and very well distributed ink, pigments into the ink, and finally the rest of the ink. You may see even chemical processes are very well defined here, and they can find different alternatives to do. Okay, so this was a real example. I would like it's from 10 years ago, so I can show you. And then it's what is the functionality of raising beef. Let's see this. I would like you. This is a 14 minutes. So I ask you please to see this video that I will play here, and I hope that you can listen the sounds, and of course I hope you don't get scared, or you are not very sensitive to some of the images and some of the concepts that are shown here. It's about meat, and you may see some not very nice images. They will warn you, but I would like you to understand how these people is trying to make different types of meat and saving the world of a lot of water for raising the beef, the meat, and also avoiding a lot of cattle, etc. Let's see. Let's see.
I'm sorry, the sound is pretty low or not hearable, and it's also pretty laggy. Difficult to watch it.
That is the question. Are we ready to that change? As you may recognize, there are always innovators that are ahead of their time, but $10,000 kilos.
Sir, we don't have any sound. The video is also lagging.
Sorry, is there any problem with the sound?
Yes, we can't hear anything.
You cannot hear anything?
No, nothing.
Okay. Let me check if you can hear and tell me just. If I can bring my okay, try to copy this link. Try to copy this link into your computer. Okay. But I
Could
will
you
try.
just share the link in the chat? Because it's not possible to copy it from the.
Okay, I will link. I will share. Thank
Yeah.
you. Okay.
Thanks.
Let me just share it. Good idea. Okay. You are smarter than me. Okay. Perfect. Okay. So let me let me get here. No. Okay. Here. Then I just okay. Then I put the link here. Okay. And you get it. Okay. This is the link. Okay. You can here. Yes. Okay. You get it, and we can see. Okay. Okay. So we will see this. You see how many thousands of animals to keep up to calm our need for beef. Just a comment about this Beyond Meat company. Just a comment beyond this from this Beyond Meat company is the provider of Burger King. When you eat a Rebel Burger King, you are eating a Beyond Meat. So they have achieved a large goal into innovation for this. Although I don't like, but I can appreciate that being provider of Burger King all over the world with Rebel Whopper is a very big leap for this company, Beyond Meat. Hmm. 2,000 people for a year. Okay, I hope you are finishing. I give you some minutes because you started just afterwards. So, but this is about this. Okay. I'll give you 2 minutes more and then we take again. Okay, let's continue. The point here, just before we start here, is just that this professor in the Netherlands sent that the fibers of his meat, fibers are almost the same, but the fibers are less have less strain than the real strain tension possibilities than the real fibers of cattle. So he thought that as we learn about our own body, the sport makes our fibers stronger and more endurable. So he thought that the cattle also move and make that and waiting and resisting their own weight, etc. So this produces a more enduring fibers. So he started to build the fibers and then started to make a process for stretching and releasing, stretching and releasing these fibers to get even closer of the real meat. So I expect that with this huge savings in mind, this could be the future for us. Okay, so again, it's learning how to build the same functionalities that are in every process, in every and understand what functionalities are more relevant and what are less relevant. Okay, let's go into our second. This is how to improve processes. Let's go into how to understand some evolution laws and at least introduce the idea of tech mining for the next week. Okay, I thank you for all of you that have sent the consent to me. I have sent the email with your emails to Georgia Tech this evening, this afternoon, and I hope you will receive some email from them. Okay, just for you to I hope for you to download the tool and the password for at least 15 days. Okay, so let's hope from next week on the software will start to work next Monday, and then 15 days for the next Monday. You will see. Well, I will explain later. Okay, let's go into the process and the evolution of technologies. This is a more theoretical part. Okay, but I will. Sure. What we saw, we started what is a technology, okay, and we saw how does a technology evolve. This is a new thing, okay, and where do new technologies originate? So we will explore some concepts about. Reminding some definitions, technology is any systematized knowledge applied to alter, control, or order elements of the physical or social environments. You may see this reminds our definition of a function. Function is any change to any action that changes, control, or maintains parameters of a receiver. So here alter, control, or order elements of the physical or social environments. Okay, so this is a good definition. That you have the citation here, and let's move ahead. The point is how systems are born and how then systems consolidate. Okay, and I will remind some of the things we saw. I think two breaks before of this course, with 2 breaks, and this is about let me go ahead and let me check. Okay, I'll see. Okay. So that's it. So let's go. Normally, how systems are born and how systems evolve. That's the point. And this is a S curve. You are familiar with the S curve. The S curve for technology progress. They say the S curve of the innovation, but it's the S curve of the progress of a technology. And because this technology is public, it is an innovation. Okay, but the point, and we will see an example of a bicycle. No, yes, it is an ancient bicycle, accelerometer. Okay, then came speed was one of the points, so they big the large front wheel. The larger the more you can speed your bicycle. Okay, and then came the transmission. Okay, the transmission was the invention of afterwards, and then came the pneumatic wheels. So we put pneumatics into the wheel, so we soften the ride of the bike, and finally we soften even every vibration and any bump in our bikes. Okay, adding shock absorbers into our bikes. Okay, so this is about, and you may have here the Celeriped and Hobby Horse and McCall's copy Macmillan rear driver, Elements Velocipede in 1866, and finally the bicycle in 1880 with the ordinary in 1876 with the transmission. Okay, the kangaroo safety, and finally pneumatic safety in 1896. Not very long, and we can see here all the elements. Okay, so we put this in the ordinary bicycle in 1876. Okay, so that's it. Okay, is there any order in the consolidation of a system? And we call here the hierarchy. You see that you can make a functional analysis, and you can assess the value of and measure the value of each functionality. But is there any? And I thought that the farther you are from the tool, the less value you have, and this is because most of the technologies have this hierarchy. We have a tool that is the most relevant of the system, and which is directly changing or acting on the object. And this is all our system is needed because this useful, this main action, the main function. And we have a transmission, some motor, some transmissions, and energy and control. And I talked you about the weapon of launching and it was just a tool. Then came the arrow transmission, because I made the transmission. I was the motor and the transmission in the stone and the control. Then came the arrow and the bow, and the transmission was the rope of the bow, and the tool was the arrow, and the force was me, and the control also me. Then came the gun. The gun has the motor, the chemical energy, transmission, the cases. The tool is the bullet, and the control is me. And finally, when we talk about guiding drones or guiding missiles, the control is contained in the same weapon. So everything is there, the head of the missile, and finally the control for the self-controlled missile or the self-controlled drones. So all the systems can be all the systems can be like this. Okay, organization of a system. Okay, but how systems evolve? This is just to remind how some things have evolved. This is a 5 megabyte hard disk in 1956. You see IBM here, and you may check what is the size of 5 megabyte. Okay, now we can see now how it's in 2005. That's micro SD memory was 128 megabyte. Okay, so 5 megabyte here, 28 megabyte, and then in 2014, 128 gigabyte. Okay, in this one, and I show you this one is just this small USB is 500 gigabyte in this small, but this all it's amazing, and this is just to show the size of this USB in 2019. Okay, 500 gigabyte. Okay, we can see that miniaturization is one of the trends in many systems. Okay, and we will I again go back to ask some questions. Where do new technologies originate? Do new technologies come from a new combination of existing phenomena and technology? Yes, we saw that the jet turbine was like this. Or about new functioning principles. Let's see this, a new effect. Let's see this. Let me check this one. Excuse me. Let me go back, and then let me go back. Okay. Let's go back and then get this. Okay, just see this. Let me show you this. You will see. There's no sound here. There's an increase in temperature, then, and when we cooling effect. Imagine this apply in a closed in a closed world. Imagine this in a closed world, that you can motor just turns with a very small energy, can turn an elastomer, and then just release the heat, and then put it into the evaporator and cool all the things. So this also is a revolution that can come in the future due to new effects. For instance, this is a classic sail ship, and this is America's, and this is a classical sail ship, and this is America's Cup sail ship. Have you ever wondered how especially these ships, can go faster than the wind? I mean, the wind can be 20 kilometers per hour, and they can go 50 kilometers per hour, because again, they are not, the effect was not direct pressure from the wind, but again, the effect of Bernoulli. The Bernoulli effect, like in the wind turbines that we saw, it's helps, they orient this and produce a large force to move the ship faster than the wind. Okay, so this is using effects that apply to new effects, apply to the ancient elements. It's like we saw this. It was the pressure, and here is the same. The Bernoulli effect, the effect of the plane, of the wings of the plane, and all the force that are moving into this direction and orienting the blades according to the speed of the turn and the speed of the wind. So it's controlled by a controller, and the controller puts the optimal angle for producing the maximum force for moving the blades of the wing. Okay, we talked already about this, but what about the uses of laser? This was in the 60s. Now we can, and these are the components of a laser. Okay, it's between two mirrors and a tube, vacuum tube with a rare gas, mean less than the air pressure, and then light that is reflecting here, and finally it's going out. Okay, so well, this is to see you. This is a new magazine, a current magazine, and where have all the lasers gone? This is the question. But the point is, we can see many uses of the laser. But let's ask again, how does technology evolve? And we can see different and see the uses of laser, thermal energy, music playing, text typing, surgery, ophthalmology, communications, transmission, mechanizing, spectroscopy, measurements, welding, payment means, and LIDAR, long range radar, is a LIDAR for detecting, for instance, turbulences into the planes. That's when the pilot advises us, we will reach some turbulences, please fasten your seat belts. It is because they have a LIDAR that can detect these turbulences before they reach them. Lithography, printers, scanners, but is that everything? Of course, we can extend the list, but what about pulsating laser? This is a new thing. This is a hot research topic about ultra short pulse laser, and we can see kill viruses, including HIV, influenza virus, noroviruses, disinfection of medicines, production of inactivated vaccines, like in silicon wafers, colliding dense beams of elementary particles, drive nuclear reactions, heat matter to conditions found in stars. All these are uses of pulse laser, and there is a leading. We have in Europe a leading researcher that I think it's in Switzerland or Austria or Germany. I in the German part of Switzerland, or I can't remember exactly, but is the most advanced in ultra short pulsed laser, and especially for killing viruses. It's now a good thing. And this is about evolution. You see, Apple in 76, and Apple in 2020, Google in 98, and Google in 2020, and Amazon in 94, and Amazon in 2020. If we can predict this, would be nice. But what there was an analyzer of patents, an examiner of patents was examining patents, and he arrived to the idea that many systems follow a path, follow some guidelines to evolve. So we can expect what a technology can reach if we know this. And he said this, the Altshuler was an examiner of patents, and he said the evolution of all technical systems is governed by objective laws. This is a very ambitious, because if we can discover these laws, we can predict our efforts. Let's see what he says in this. Okay, so these are some of the laws: ideality, controllability, dynamicity, coordination. We'll see. We have talk about ideality: less components, less burden, less energy, less materials, and but we keep functionality. And in the end, remember, we remove the need for a lawnmower, because the lawn can control by itself the height of the lawn. Okay, so this is the ideal point. There is no machine, but the function is achieved. So this is about ideality. But what about controllability, dynamicity, and coordination? Let's see some examples. This is about segmentation of substance and fields. This is one part, one sub-law from controllability and controllability. Okay, and this is substance segmentation. And one example is about this. First, we have a monolith. Okay, a monolith. Sorry, we have a monolith. Then the system evolves into a segmented monolith. Okay, then the segmentation goes deeper, and then we have a powder or even a liquid, because it's made of fine pieces, and it's like a powder, or it's even, because it has some diluent or some matrix, we can have a liquid here. Okay, so this is what the law may see. Okay, then comes the use of ions, okay, and gases, and finally the use of energy, fields, magnetic fields, electric fields, pressure fields, whatever. Okay, so from a big piece, small pieces, then powders, and then ions or gases, and finally not presence, sometimes not presence of this one, of these elements, but presences of field. So let's see, for instance, one example of this trend, of this sub law. For instance, in writing. if you remember the typing machine, you just press one letter and then a lever just moves and stamp the ink into the paper. Okay, so you have to write like as you do into the Word, but with a machine, and each button, each letter in your buttons in your keyboard was a lever for printing the letter. So you write, and remember, 300 and specialist typing people was able to type 400 characters per minute. Okay, so they wrote very quickly with the QWERTY keyboard, the QWERTY keyboard, and so you could write. Okay, so let's move again. And what happened afterwards? We went into the matrix printer. Maybe you don't know this printer, but this was very each character was made from small dots, so you can have only some dots, and with these dots draw any character. Matrix printer were very strong, very reliable. No problem of ink, no problem of anything. All the time worked, but evolution is like this. Evolution just get you rid of the market. So matrix printer were not enough elegant to write, to make and when we progressed with the WYSIWYG, what you see is what you get. You remember I talked about it. What you see is what you get. It was a major leap into the computing industry and approach us to the final state like today. Okay, so then came we segmented even more the character, and we put the inkjet printer. So these dots are made very tiny, and so we put it into a diluent, and we just put the ink particles, and these ink particles are ejected and printed into the paper. Okay, so I work for a large company which manufactures these large printers, and they just, for instance, they boil the ink inside that printer. And when it boils, it just ejects a drop, and then cools and boils again, and cools and boils, and make this 100 or 1,000 of times per second. So it's and this is marvelous, and this is how we can print with our jet printer. Okay, then came ionization printers, and finally came no ink at all in the printer, but energy, and this energy is the laser printer. So we just our element just make this, and the toner or the same paper gets printed in special paper. Some papers need also ink, but at the beginning there was a paper without any ink for the printer. Just using the laser, we can draw the same. So you may say it's the same like this, but in the printing process evolve like this. Let's see dynamization, for instance. This is dynamicity. It's another. Things are static and become dynamic. So what is this? You may see, for instance, this is about the first mobile phone, a system, immobile system, a system with one joint, a system with many joints, a completely elastic system. Remember the ball pen I showed to you? then the use of liquid or gas, and the system, the use of fields. It's similar to segmentation, but this case is about degree of movements, okay? Degree of freedom degrees, okay? For machines, for whatever. Let's see, for instance, in a why the you may think why some saga of movies follow the order that they follow. For instance, the movie of Terminator. How was how was the first Terminator? It was a mechanical Terminator. Then came the second Terminator that was a special alloy that can move like a liquid or like a complete elastic system. And then finally, Terminator 3 was a lady with a field for producing the weapon of a field, using fields for this. Okay, this is not a random, they follow the same path. But what this prediction can tell us to a car manufacturer, what this can this prediction tell to a car manufacturer? When you open the door of a car, you in cars of 10 years ago or 15 years ago, you just could have the door of your car closed or completely open, okay? And there was no medium states for your car, or your car was the door of your car was closed, or you open totally the door of the car. Then came the new cars, the cars 10 years ago, and from now on, cars have different states, intermediate states for a car. That means for a door. So you can open the door of the car and put it into a 1/4, then 3/4, and finally totally open. You mean you get a steady state in 1/4 of open, and steady state at 3/4, and finally totally open, 100%. So there are different states here, different joints, different steady states here. So what could be the next move? What could be the next move? We have only one totally open. We have now 3, and the next could be many different states. And what about using liquids or gases to reach this? This reflection was the reflection of a car manufacturer. It's MGI Coutier. It's a manufacturer of hinges for the car doors. Okay, he is the manufacturer of the hinges of the door of your car. Okay, so you probably didn't realize your car has hinge, or maybe you think, but pay attention to the hinge of your door, the door of your car. So they thought, how can we reach a door? How can we reach a hinge with a door that can stop whenever you put it? I mean, you can open just 1/10, or you can open just 1/15, or you can open just 1/27, or whatever of all the, whenever you want it to keep steady, you can leave it, and it gets steady and stop at your desired degree of angle, your selected angle. So this is not many joints, but completely elastic system. It's an infinitum of states, infinitum of joints. It's a completely elastic. You can open your door at any angle, and it will remain steady at this angle. Of course, you can do a very tight hinge, but it could be very difficult for you. You have to do a long force, a strong force for opening the door. In that case, you open the door with a large, very strong force, and you can take it there. But manufacturers thought doors should be very easy to open and to close. But once the door stops at any angle, it will remain stopped. And so they started to think, because they saw this, and they saw we should move into this direction. And they proposed one patent. One patent just proposed one system, but they have more. This is a patent. So this is the hinge of a car that has, this is you open the door and this gets fixed. Okay, it's not movable. This is a plenty of liquid. Okay, plenty of liquid here. And when you open, you pass the liquid of this chamber to this chamber and vice versa. Okay, so they have here some valves with a pressure. So when you don't move the door, the pressure just closes this, and you cannot move the door. When you just press a bit, you open the valves, and then the liquid goes from one part to the other, and then you can move the door. So this is one of the hinge that is present in some luxury cars. Okay, this is one hinge that it's present in luxury in one. Of course, they have other patents instead of a pressure with a magnetic solution here, etc. But the main concept came from here. We evolved from this to this, and we should evolve to the next one. Okay, this is the point of this trends of evolution. This is the point of trends of evolution. This is what I show. This is about many joints, then the liquid, and finally the fields. Okay, this is what I just put. But what about, can we have the stocks are elastic. Okay, can we move ahead and have liquid stocks? This is what a Japanese manufacturer made. It's about, the next step is just about liquid stocks and spray stockings. Okay, spray on stockings released in Japan. This was in 2003, was launched a stocking. Okay, wash off with soap, and it's like this. Okay, what's the function of a stocking? Is just decorating the leg and isolating the leg from the cold environment, or releasing the vapor of the sweat because of the warmer environment. Okay, but these are and a good looking finishing for the legs. So this is what the company just thought and rethought how you can get this. So they made like this. and this was in 2003, okay, but now they have evolved this, and this is about today, okay. So you can air stocking is the point, and you can see many different colors and different finishings, but it's the same effect as and is isolating like a stocking, normal stocking, and this is about, okay, again, and does a shoe follow the dynamization law, or do shoes follow the dynamization law? Maybe that means that when you have a shoe, it is static. What about a moving shoe? Just this is about this shoe. This shoe is for kids, but it can grow as your kid grows. Okay, so this is about this, a dynamic shoe. Okay, is the point. It's 10 and then 11 and point and 12. Okay, the same for skating, skaters, skates. It's the same for skates. They are dynamic for kids that grow their feet. Okay, this is about. And what about a car? There are also dynamic cars. So things are static and become dynamics. The fork of a bike was static, and then came shock absorbers. So the fork of a bike is dynamic right now. And what about other examples of laws? This is the mono bipoly, is another law in the transition to the super system. It's about lenses. Okay, we can see mono. We can see then the bifocal lenses. Then the Barilux or multifocal lenses, and finally the contact lenses. Okay, and what about another of the transition to the super system is the hybridation, and we will finish with this. This is about a CAT image, a computer-aided tomography, and in the middle we have a positron emission tomography image. Okay, so this was the state of the art until the year 2000. It was invented in 76, and it was invented also by that year, and many hospitals had a PET scan and a CAT scan. So a CAT scan reveals your structure, but not very well cancers, for instance, or tumors or whatever. Instead, PET images reveal very well tumors, cancer, etc., but poorly the parts of the body we are reflecting. So by combining the two scanners in a hybrid system, allow to obtain the advantages of both scanner and superimpose them. And you can see here the body is well defined, and also the tumors are well defined. So doctors can see where things are occurring. Okay, what things are occurring and where are they occurring. So the benefit of this plus the benefit of this. But the point is that this was a 2000 invention, and the CAT scan was invented by Gottfried Neuhold Hounsfield in EMI, Electrical Musical Industry, in 73, and also the positron emission tomography was invented by in the UCLA in 74. Michael Phelps, not the swimmer, but more ancient Michael Phelps, and just which almost exhausted all its conceptual possibilities. Then until 2000 was invented the new combined scanner, PET and CAT at the same time. It looks like a simple thing, but you see, 30 years for just moving ahead. Hybridization is one of the laws that is fine. If we follow the laws, we can predict that things can be hybrid and just move this. So sometimes things look simple, but it takes 30 years to come to our world. Okay, and this is about this is the in 2000 a new hybrid whole body scanner. This in 2003 they perfected and combined the two machines. At the beginning, two machines were one at the side of the other, but then they combined the two into one machine. Okay, and this is how it works. Okay, this is the machine right now. Okay, we finish here, and I will send you an email regarding what is the idea of tech mining. And so next week you will receive, I hope, before we start on Monday next week, you will receive the email for discharging your tool about tech mining, and we will try to work on this. I will try to download information for each of you. So I have, for instance, made it for energy harvesting and for cleaning robots, and I will make it for other works of you, and you could work with it and get about intellectual property, etc. Thank you very much, and see you next week. Bye.
Thank you. Bye bye.
Goodbye.
Houdoe.
Bye.
Bye.
Is there any question?
Yeah,
Okay.
sorry, I had a quick question before you go. I was just wondering about the content of the report. I know you've said before that's supposed to have 3 main parts, but would it be possible to get like a bit more detail about what the report should contain, maybe in an email or like in a document?
About the document? Okay. Yes,
about the
I will.
report, like what it should contain.
Okay, yes. Okay, I'll try to do. Okay, perfect.
Okay,
Good
thanks.
proposition. Thank you very much. Okay, I will do. Thank you.
Thanks.
Bye.